Okay, so let's start with a quick review of what we did in the last class. Let's start with the singular value decomposition. Before that, how was the quiz? Difficult, easy, medium? Medium? It was okay. Anyway, we'll discuss the solution next week. The TS will, or I myself will discuss the solution. And then I will hand over the evaluated answer scripts. Okay, so let's get started. Quick recap. So last class we looked at a very important concept in linear algebra, very useful in many domains, especially data analysis, which is called the singular value decomposition. It's very important because of several reasons. Of course, it has a lot of use cases because unlike eigenvalue decomposition, there is no condition under which you can decompose this way. You give me any matrix A, I can write it as product of three matrices, right? U and V being unitary matrices, right? That means U Hermitian is U Hermitian U, which is identity. That means all the columns are orthonormal, all the rows are also orthonormal. That's what it means. And sigma being the diagonal matrix with diagonal entries being non-negative, it's greater than or equal to 0, and they are called singular values. Okay, and we related the singular value decomposition to eigenvalue decomposition. How do you find singular value decomposition using eigenvalue decomposition? So one way is you look at A Hermitian and A Hermitian A, do eigenvalue decomposition. You will get the corresponding matrices. The matrices that you get correspond to the left and right singular vector of this. So okay, that is another terminology. So for example, if you look at this, right, so the U matrix, the columns of U matrix is called the left singular vectors. Okay, of course, for eigenvalue decomposition we call it as eigenvectors, so here we call it as singular vectors. Okay, so obviously the columns of V we call it as the right singular vector, and U is called the left singular matrix, V is called the right singular matrix. Okay, yeah. Then I think after this we started looking at principal component analysis, but we will revisit that again today. Okay, so let's get started here. Okay, so let's start with what is known as principal component analysis. So let's look at the setup. The setup is as follows. So you have data, you know where the data comes from, right? For example, you are doing spam versus non-spam classification problem. You take an email, convert it to a big vector called feature vectors, right? So that's what I call as data. So either that feature vector, or if you have a label for it saying spam or non-spam, I will call that set as a data set. Okay, so for example, you have x1, x2, etc., xn. Let's say it belongs to, or D is the dimension of your feature vector. That means you are considering D features to convert, basically to extract the feature. Okay, so you are looking at D features here. Okay, so you have this data. So typically, in many applications, this D is very large. For example, if you look at spam versus non-spam, you collect all the bag of words, right? And then count the number of words, each word appearing in a text. So that is what you do typically in your NLP sort of problems, right? Natural language processing. So that D, for example, if you consider 20,000 words, then D will be 20,000, right? Huge. Okay. And that means if you look at x1, there are 20,000 numbers, and you have to do, if you want to do some data processing or data analysis, then you will be doing 20,000, you'll be dealing with 20,000 numbers. In many other cases, D is much larger. So we want to somehow reduce this for computation purposes, right? Without losing any information about the task. So what is the kind of problem that you will solve here? So essentially, think of, obviously I cannot write these points in n dimension or d dimension. Think of it as higher dimension, very high dimension. Now I want to reduce it to a lower dimension, right? So what are the ways and what kind of problems you will solve? Okay, so let me look at an example. Suppose I look at 3 dimension. Okay, so let's say 3-dimensional space, and you have let's say 1,000 points, right? What might happen is, these all 3,000 points could be on a plane, right? So all these, okay, maybe some of them are slightly above, some of them are below, but roughly on a plane, right? So supposing this is the case, do you really need to deal with 3-dimensional space? No, right? So if I think of this plane as, obviously a plane is a 2-dimensional space, right? So if I can somehow think of those points lying on a plane, then I, essentially by doing appropriate transformation, I can think of these points as 2-dimensional, right? Without losing any information, right? So now the question is, it's easier to say by looking at diagrams, but how do you convert that into math, right? That's the question. So now, what do you think you do? So essentially, what you end up doing is you have to project onto a subspace. Okay. Before that, a small aside. For example, in 2 dimension, this is a subspace, right? A line passing through origin is a subspace. In general, any plane passing through origin will be a subspace. But what about this guy? What is it called? What I'm going to do is I'm going to take a subspace, give a small kick, right, in some direction, so it doesn't pass through the origin. How do you write this, by the way? So what is it that you are doing? So every point, for example, if I take this vector as let's say u, or u, all that you are doing is you are taking every point and adding a vector u to it, right? So you take every point here and add a vector u to get this, right? So how do you write it mathematically? This is, let's say, vector space V. It's a subspace. What is this space? It's V plus U, right? Which is set of all V plus U such that V belongs to V, right? That's all. What is this called? Do you know? Any idea what this is called? The name. So what kind of a transformation is AX plus B or A something plus B? It's called affine. Okay, so this is an affine set. Okay, anyway, this is just a name. So in other words, you take any plane in n-dimensional space, it's either a subspace or it has an offset. Okay, so now you have these points, right? All these points. It may not lie on a plane. It will be around a plane, right? But I have to approximate it by a plane. So what do? So this is the problem that I would solve, right? So first of all, I want to project it onto some subspace or some space, right? So that means each point xi I take, which is d by 1 vector, right? D-dimensional space. I project it onto some space P, Px. So P is a matrix, which is, let's say, some k by d. K is something that I'm going to fix beforehand. Let's say you have some idea of how the data looks like. You know that it's on a plane in some k dimension. You have some rough idea based on the physics of the problem. So now I want to bring it down to k dimensional, not d dimensional, right? So obviously d is much larger than k, right? This is the assumption. Otherwise, it makes no sense, right? If it is 10,000 dimensional space, you are projecting it onto 9,998 dimensional space. Doesn't make sense. Okay. So now you have Pxi, right? Now, if you look, so this Pxi will project onto some subspace. It can be anything, right? For example, it can project onto 3-dimensional subspace or some other 3-dimensional subspace and so on. But I want this to be as close as possible to xi itself. If you go back, for example, you have a point here on this plane, and if your projection is P corresponds to projecting onto this plane, this point is same as Pxi is same as xi, right? It will lie on that plane itself. So the distance is 0, right? Norm difference is 0. But if it is here, for example, all that you're doing is projecting it here. I mean, you're just looking at the closest point.